Okay, so we're going to start looking at the second half of derivative applications. We're going to look at the extreme values of a function. So let's take a look at some definitions that we're going to be using and so forth. So one of the useful things we can learn from functions derivatives, whether the function has any maximum or minimum values on a given interval and where they are located. These maximum and minimum values called extrema, just the plural of it, come in two types. You have the absolute extrema and the local extrema. Other names for these are global or relative. This one over here, I basically use absolute extrema all the time, but over here I'll interchange these two words just because I'm just used to doing that. So relative extrema or local extrema and absolute. So what is the difference between them? Let's take a look. So here's your absolutes, max and mins, basically the same definition, just one's a max and one's a min. So we have a function defined at c, so f of c is an absolute maximum value if and only if the y value at c is greater than all other y values for all the other x's in the domain that we're looking at. Okay, so basically it means it is the absolute highest y value. And then the minimum is obviously the same thing, just being the lowest y value of all y values in your domain, from the x's in your domain. That is absolute. What is local or relative? So in this case, the local or relative is, let's just look at the maximum here. So this y value is a local maximum value of f if and only if it is the largest value of all x's in some interval around the point C. So this basically boils down to this. If you think about polynomials and stuff as our example, if I have a polynomial like that, and it goes on forever and ever in both directions, oops, you can see that there is no bottom to this. There's no way down here that's ever going to stop. It goes down forever and ever. So this is no absolute minimum. Same thing with this direction, going up forever and ever and ever. There is no highest value you can come to, so there is no absolute maximum. But if I look right around this place, in here, in this little interval right here, well, there's a number up here. There's some C value right here in this little interval, right there, where around here, that is the highest value of everything around that. Not for the whole thing, but just in that little small interval. In that interval, so this is what's called a local maximum. And then the same argument down here, there's a spot right here that we can call. So this is C1, C2 over here, just with marked it. Here's an interval right here. And these points have y values here. And this is the lowest value of all the y values in this little interval right here. That is a local minimum. That's what it is referring to. In some interval containing C, there is a y value here, there's a y value here, and this is the lowest one of all. Now, these are very important to us, okay? We're going to be looking at this quite a lot in this section. The next word here, the definition is a critical point. The points in the interval, the points in the interior of the domain of a function where the derivative is 0 or undefined. These points are important because relative and absolute extremas can, but they don't have to, occur at such points. So let's talk about this and think about it for a minute. We'll talk about the undefined in a little bit. Let's talk about when a derivative is 0. Well, what does it mean to have a derivative that is equal to 0? Because derivatives represent slopes, then we're saying that the slope of a tangent line at some point is 0, which makes it a horizontal tangent. And you'll notice right at these little relative max and min points right here, they have horizontal tangents. And so that's how we're going to find them. Okay, so critical points are going to be huge in locating and finding relative extremas and also absolute extremas. Okay, so let's continue on. Let's look at some examples here. Let's see if we can figure out some stuff. I have a couple examples here. Let's see if we can identify some extremas. So here's our picture right here. And we want to identify all the extrema. So we got 5 points over here. So let's address each and every one of them. And so the first thing you should look at is peaks and valleys like this. Peaks and valleys are your relative extremas. Okay. Also, endpoints can be relative extremas because the interval containing that point, this is the smallest one in some little interval around it. Yes, there's no other side over here, but it is the smallest one in an interval that I can place this point into. If I pick an interval around it, this is the lowest one. That's what a relative extrema means. So we can come over here and we can say that points A, C, and E then would be considered relative extrema, relative minimums. I'm going to abbreviate here. They're relative mins. Okay. Well, then what is B and D? So B and D would be relative or local maxes. Okay. Now look at D. D is the highest Y value of this entire picture on this entire domain that we're looking at. So that makes D, not only is it a relative maximum, it is also the absolute max of this function in this domain. Well, likewise then, what's the lowest value that I can have here? Well, it would be A. And so A, not only is it a relative minimum, it is also the absolute minimum. And that can happen quite often. So a relative maximum could actually also be an absolute maximum, but doesn't have to. All right, you'll see examples of all that kind of stuff as we move along. So what else do I can see from all this? What else do I know? Well, we talked about critical points. Okay, critical points are points on a function where the derivative of that point will be 0 or undefined. And so those are going to occur at peaks and valleys. So we can see from our picture here that I'm going to have 3 critical points. B, C, and D are critical points because why? Because the derivative is 0 there. Okay? Now, what about these endpoints here? Well, we just don't know. For A and E, the derivative could be 0 there, but we can't tell. They're just the endpoints. So they are endpoints. We do not know if the derivative there is 0. Okay? So we do know for sure that these are. I'm saying that these can't be 0. Okay? I just don't have enough information at this point. Okay? So let's take a look at another example that I have. Here's this one right here. Do the same thing. What are the extremas on this one? You can pause and try and write out your own just to see if you can understand those. So I'll give you a few seconds here to pause it. Okay, so hopefully you paused and you figured out and wrote out your own stuff. Here's what I would have. So if I look over here, what do I have here? I have A and E and C are all relative maxes. So A, C, and E are relative max, but C is the highest one. So C is also the absolute max of this function. What's the lowest value here? That's B, isn't it? B is the lowest one of this entire thing, but D is also a low one here. So B and D are both relative minimums. So B and D are relative minimums, but B is also the absolute minimum. It's the lowest value of all the Y values. But look at how this graph looks. See at B, we have this little corner here, and D, we have the corner here, and we talked about that. So what's the derivative at these points? Well, when I have these little corners or cusps like this, remember the derivative is not defined. So that means B and D occur where the derivative is undefined. So you can see, as we did for critical points, these are also critical points. And these also established a relative maximum min or absolute. So that's why we need to look for when the derivative is 0 for these situations and when the derivative is undefined for these situations. So when you're looking for critical points, that's what you need to do. Another thing about critical points too is the fact that if it has a relative maximum min, it's going to occur at a critical point. That's the important thing about critical points. Very, very huge information. Okay? So let's take a look at something else I want to show you. Not all functions have a max or a min, either absolute or relative. This graph right here has a vertical asymptote at 0, a horizontal asymptote at 0. This is the function 1 over x. There is no highest value. There is no lowest value. There is no point that becomes the lowest in any interval because this piece is always decreasing. This piece is always decreasing. So it never has a max or min. Here, the endpoints are not included. Since the endpoints are not included, there is no maximum value over here. No matter whatever point you pick for a y value, as I get closer and closer to this number right here, whatever this is, the closer I get to it, the higher the y value goes. And it never stops. No matter how close I get, the y value will keep getting larger. Even so small of an increase, but it's still increasing. So there is no relative max here. There is no absolute max here. And likewise for this piece down here. Okay? So just keep in mind, you don't have to have any of those. Just be and kind of start making a catalog of situations so that you can address them in a little bit later. Okay? So all of that conversation here with this, right, no endpoints and there's no absolute max or min, well, there's got to be something we can use to help clarify all this, and there is. It's called the extreme value theorem. Okay? Extreme value theorem, we use EVT for short. Okay? And this is what it says. It says, if a function is continuous on the closed interval from A to B, the function has both an absolute maximum and an absolute minimum on that interval. See, this one right here did not have a closed interval. This is an open interval, so it doesn't have to have one. It could, but it doesn't have to. Okay, so some of these other ones over here that we talked about originally, see, when I have these endpoints here on the end, this makes it a closed interval. So when I had this closed interval here, I had both an absolute max and an absolute min. Same thing with this example right here. I had dots on the end. This is a closed interval, and so it definitely had an absolute max and an absolute min. That's what the extreme value theorem is telling you. It will have both if you have this closed interval. This is a very important theorem. You're going to use it quite often. You want to make sure that you understand the conditions to use it. The function has to be continuous on a closed interval. Okay, then it will have both an absolute max and an absolute min. What if it's not continuous on a closed interval? Does that mean it can't have an absolute max and a min? No, that doesn't mean that at all. Okay, nothing says I can't have them on other kind of intervals. What this is doing is it's guaranteeing you to have both of them. If I have a closed interval, you are guaranteed to have both. That's what it means. This is a very important one, okay? So let's look at some examples here to help us illustrate this. I'm going to show you some functions. These are the functions on a closed interval. We have to determine whether or not, because part of using this extreme value theorem is you have to recognize the conditions to use it and then understand if I have a max or min. So the first thing you have to look for is this function continuous on that closed interval? If it's yes, then you know you have both an absolute max and an absolute min. If it's no, does it still have one? Is what you're looking at then. So let's take a look at some of the examples here. Just going to lay them out here for you. So here's the first three. So this one we kind of talked about already, but remember, we're only looking at from 0 to 6. So don't worry about any of the graph that goes beyond 0 and 6. So from here, there's like a dot right there. Over here, there's like a dot right there. So first off, is this continuous on the closed interval? Well, I have a vertical asymptote going right through the middle of it, so the answer to this would be no. There isn't one. Okay? But does it have an absolute max and min? Let's take a look. So it's not continuous, and there is no absolute max and min because this thing just keeps going up forever, and this piece is going down forever. So no absolute max or min. This one we already kind of looked at before. Is this continuous on the closed interval? No, it is not continuous at the endpoints. Okay, so it does not have an absolute max or min. We already established that one up here at the top. Okay, what about this one over here? So this one has a from 0 to 6. We have a vertical asymptote in the middle, so it is not continuous. But at 6, it actually touches 6, 0. So this point right here is 6, 0. Okay. So the question that becomes is this. It's not continuous. Does it have an absolute max? No, the arrow's going up. It tells me it does not have an absolute max. But because it touched right there at 6, 0, okay, then what do I know? I have an absolute minimum there. Okay? I have an absolute minimum there. Had a horizontal asymptote at 0. This is going to get closer and closer to the 0 over here. But at 6, it touched. So that's where it's the absolute minimum is going to occur. Okay? So I have another one over here. Let's take a look at. Kind of revealing the answer here a bit. So sorry about that. Let's see if I can cover it up before you see it. What about this picture? Again, going from 0 to 6 over here. Okay, forget that the arrows are going up in that fashion. Am I continuous between 0 and 6? No, I have a discontinuity right here at 4. But do I have an absolute maximum at between 0 and 6? No, right there and right there are endpoints. Okay, so what does that tell me? Well, I don't have an absolute min. There is no smallest number, but I do have an absolute max, and that should occur at 0. Because this endpoint right here is larger than this endpoint over here. So I have not continuous. There is no minimum. There is no number I can get to the lowest, and you have an absolute max at 0, the endpoint of that thing. Okay? So let's look at a couple of ones. I want you to try some things out over here. Let's start with this one right here. So you can go ahead and pause your video right now and take a few seconds here and try and do that one and list this one on your own. This is a dot. This is a dot. That's a circle, open circle there. And pause it. So I hope you paused it and tried this on your own. Let's see what you got as an answer for this one. So are we continuous? No, we are not continuous at 6. Okay, we are not continuous at 6, so it's not continuous. Not continuous at x equals 6. But what? Do I know anything else? Well, do I have an absolute minimum value? Is there a point, is there a y value that is the lowest, lower than all the other y values? Yes. So I have an absolute min at x equals 0. Is there a y value that's taller or larger than any other y value in this interval between 0 and 6? And the answer is yes. That one. So you'll have an absolute max at x equals 6. Okay? So let's take a look at another one. This one again is a pausing one for you. This time I want you to draw a function with these conditions. I want an absolute maximum at 2. I want an absolute minimum at 4. And I don't want it to be continuous at 0. Okay? Not continuous at 0. Absolute max at 2. Absolute min at 4. Pause the video and see if you can draw that picture. So hopefully you paused it and you tried to draw one on your own. If not, here's what I came up with. Again, there is an infinite number of possibilities that you could have drawn. Just because you have something different than mine does not mean that you are wrong. There's that. Okay, here's 0 over here. I need a maximum at 2. So I'm going to put a dot up here for 2, and it's going to be the highest point of them all. I need an absolute minimum of 4, so I'm going to put a dot up 4, and that's going to be the lowest point of all. 6 just has to have something over here between those two heights, so let's put a dot there. And at 0, we have to be not continuous. So that just means I need to have an open circle here at 0. And you can draw whatever you want from this point. You can draw it however you want. There's no one way to draw it. You just, I can draw, I think what I did here is I drew this, and then I did some weird stuff, and I do a little corner here, and I came down here to like a parabola, and then came over here and just did something like that. So there you go. That's a possible picture. Again, there's many other ones that you can have. Okay? So, one more example we're going to be looking at in this video right here, and this is one I want you to explore also. Okay? So you go ahead and pause after you read this question here, and then you see if you can figure out what each one of these are and explain your reasoning. And then I will come back on and I will show you my reasoning and explanation for all those. Okay? So which of the following functions has an absolute maximum on the closed interval from -3 to 3? Explain your reasoning. So take a moment, look at all those functions, and tell me which one you think will have an absolute maximum on that closed interval. Okay, let's come back to this and take a look. The first function, the cosine graph. Well, you all know what a cosine looks like. Starts at 0, it's at 1, it comes down, does this little thing like this, and it continues on in this fashion from -3 to +3, right? Sure enough, I'm going to have a continuous function on a closed interval. It will have an absolute max and an absolute min, and those are usually going to occur at 1 and -1, but it's not quite -1 down here, so it'll be a smaller number because you're not at pi over 2, so I'm not sure exactly where it's going to be, but it's not necessarily at those values. But this one does indeed have an absolute max. Okay? What about the tangent? Well, if we look at the tangent graph, we all remember this one has vertical asymptotes at pi over 2s and stuff like that, and the graph comes up and does this. Okay? So where is -3? It's like pretty close to -pi. Remember, pi is like 3.14, so -3 is almost just slightly shy of -pi, and this one over here is slightly shy of +pi. And so what's going to happen here is you have another vertical asymptote here, okay? But it doesn't matter. This one right here, even though this one come up and stop at 3, this one does not. So this one makes it continue on forever in an upward direction. So there is no absolute max, and which is what we're trying to determine. And it's not continuous on that interval. What about these other two over here? These other two I kind of graphed on a calculator so you can see them. So -1 over x squared, okay? If I have the closed interval, I have it right set up at 3.5. So right here would be where it would end, and there would be a dot there because we have a closed interval. And over here we would have a dot there. So does this graph have an absolute maximum? And the answer is yes. It's going to occur, even though it's not continuous in the middle. Okay, I have a vertical asymptote here. I'm asking for an absolute maximum, and it will have one whatever that value is at 3. So if I plug in 3 in here, I'm going to get a -1/9. So that is the maximum value of this curve at the endpoints. So this one does indeed have an absolute max. What about this one over here, the sine? Well, we can see clearly that it's not going to be continuous at 0 because you can't plug in 0. And this is where you get that little oscillating action going on in the middle. Okay. So it's not continuous, but if I drop it off at 3, So again, I'm at 3.5 over here. So I put a dot here and a dot over here, then I'm going to have a max and an absolute max. It's going to be up here somewhere. See, because the graph does not continue upwards without bound. It bounds right there at that point. That's probably the highest point. And so that's going to be my absolute max. So this one has an absolute max. This one had an absolute max. This one did not. And this one over here did. Right? So that's our conclusion for this video. We will continue this process in the next.